we have learned the definition of correlation, and correlation requires the calculation of covariance. Now here again we have the joint probability mass function that belongs to random variable x and random variable y. In this table we have the joint probability mass values. We are going to calculate the correlation of x and y this time, and then after calculating the correlation, we would like to comment on the linear dependence between x and y, what type of dependence we have, and what is the strength of that dependence. Is it a positive dependence or negative dependence? We would like to see that. Now, the correlation between x and y. The correlation between x and y is formulated as the covariance of x and y divided by the square root of the variance of x and variance of y. And if you remember in earlier questions, we have already calculated the covariance of x and y, which was equal to 0.15, and the expected value of x and expected value of y was 1.75 and 1.8. Now, we would like to calculate the variance of x and variance of y now, so we can have a complete information on this formulation. And in order to calculate the variance of x, I am going to subtract the square of the expectation from expected value of x squared, and that makes me calculate the expected value of x squared. Now, the marginal probability mass function of x is this, and we are going to multiply the square of the possible values that x can take with the respective probabilities and sum them up, and that is going to give us the expected value of x squared, which is 1 square times 0.50 plus 2 square times 0.25 and 3 square times 0.25. That is 3.75. And if you subtract the square of the expectation of x from 3.75, you get 0.6875 as the variance of x. Just like that, because we know the marginal probability mass function of y, we can compute the expected value of y squared and then the variance of y as 2.76. Now all we need to plug in this variance of x and variance of y in place of this formulation. One common mistake that is made by the students when they are solving this question, they forget to take the square of the product of the variances. So square in this formulation is usually forgotten. Be careful. Do not forget to take the square of the product of the variances. And that is going to be a 0.11 approximately. The correlation between x and y in these random variables, in this joint probability mass function, is 0.11, which means the linear dependence between x and y seems to be a positive linear dependence. However, because this value is not very close to 1, in fact, it is much more closer to 0, we should say that it is not strong. Okay? So there is a positive linear dependence, though it is not very strong. Now see that if we have the random variables that following the joint probability density function, 2 minus x minus y. So what is the correlation for these random variables? Again, we are going to calculate it, and we are going to use that to comment on the relationship between x and y. Now, if you remember again the previous questions that we have solved in the previous hour, we have computed the marginal probability marginal probability density function of x and marginal probability density function of y. And we have computed the expected value of x and y respectively for these marginal probability density function values. And we have computed the covariance as minus 1 over 144. So we have commented that there's a negative linear dependence relationship, but to make a comment on the strength is impossible when you look at the covariance. Now, what I need to do is to have a understanding about the strength of the linear dependence. I need to calculate the correlation, and the correlation requires the computation of the variances, marginal variances of these random variables. Now, in order to compute the variance, again, I need the expected value of x squared. The expected value of x squared is x squared times the marginal PDF of x integrated through the whole possible values of x, which is from 0 to 1. And that integral will give us a 1 over 4. And in order to compute the variance of x, I am going to subtract the square of the expectation from 1 over 4, which is going to be equal to 11 over 144. So the variance of x is 11 over 144. And with the same reasoning, because the probability density function of x and y are the same, just like their expectations are the same, their variances should be the same as well. And the variance of y is also equal to 11 over 144. And when you divide minus 1 over 144 to the square root of the product of the variances, you get minus 1 over 11, which indicates that, again, there is a negative linear dependence relationship between x and y. However, that linear dependence is not very strong as well, because this value as well not very close to minus 1. It is much more closer to 0. Minus 1 over 11 is much more closer to 0. Therefore, though we see a negative linear dependence relationship, so we cannot say that these are independent. They are definitely dependent. However, that dependence relationship is not very strong.